Okay friends, welcome to All Chemist Official. Today we will learn about subtopic which is first order reaction. It's based on uh, chemical kinetics chapter. For this chapter I have referred Ncert textbooks for the CBSE board. CBSE board, okay, 12th standard chemistry, okay. And here we begin. Before I start this video lecture, I want to let you know that I want to let you know I want to let you know that this is a bilingual lecture in which both Hindi and English, both language will be used for this video lecture. So here let's begin. First order reaction. In this sorry, First order reaction. In class of a reaction, the rate of the reaction is proportional to the first power of the concentration of the reactant R. For example, ठीक है. Now what is the rate of the first order of reactions? तो रिएक्शन का रेट प्रोपोर्शनल रहता है रिएक्टेंट का कॉन्सेंट्रेशन का फर्स्ट पावर से. दैट मीन्स दिस फर्स्ट ऑर्डर ऑफ रिएक्शन इज ऑफकोर्स डिपेंडेंट ऑन द reactant concentration, okay, and it is proportional to first power of the concentration of the reactant R. For example, R gives P product. The rate is minus dr upon dt is equal to k k bracket R. So rate is what? Rate of decrease in concentration of a reactor with respect to time equal to K multiplied by R concentration of R. Now the R in a bracket signify the concentration of a reactant. So we shouldn't misunderstand that the this R in the brackets have some vag or futile value. Whenever there will be anything, for example the R within the bracket, we should always consider that this is signifying us that this is the concentration of the reactant, okay. We shouldn't assume it that the value of this bracket in a R in a bracket is have some vag value, or it is we are doing it to uh, for any decoration or for to make it the handwriting clear. It's not like that. The value are not a vag. The reason that why the R is in the bracket, because it signifies that this is a concentration of the reactant. So differential concentration of the reactant upon rate of concentration of reactant is equal to minus K multiplied by dt. So dt and rate of reaction is cross multiply, okay, cross chain. Integrating this equation, we get, when we integrate this equation, what we get, Ln rate of a concentration of a reactant equal to minus Kt plus I. So after doing integration, differentiation is gone. Now it become into ln rate of concentration of reactant is equal to minus Kt plus I. Now again I is the concentration of integration, and its value can be determined easily. Now I is once again the integration constant. Its value can be determined easily when t is equal to 0. R is equal to R is equal to R in a bracket with the power of base 0, where once again this concentration of a reactant to the base power 0 signify initial concentration of the reactant, okay. Whenever there will be the base to the power 0, we should always consider that this is the initial concentration of the reactant. Therefore, equation 4.8 can be written as ln in R in a bracket base to the 0, which is showing log to the power, which is showing ln log rate of initial concentration is equal to minus K multiplied by 0 plus I, because time is 0 and at that time initial concentration of reactant will be might be much larger in amount. Okay, so ln in bracket R in bracket base to power 0, ठीक है, so is equal to I, ठीक है. Substituting the value I in equation we get, now in place of I substituted by ln R0, that is ln log initial concentration of reactant. Okay, so the equation become ln rate concentration of reactant equal to minus K T plus ln R0. Okay, then rearranging this equation we get ln R upon R0 minus K equal to 1 by T ln. Okay, now it's see your ln R in the bracket 0 upon R in bracket. See, there is a difference that in this equations this negative value was there. To avoid this negative value, whatever was there, the numerator and the denominator got exchanged. Okay, the equation turn opposite to avoid the negative value, and therefore K become the rate constant of first order reaction, because K equal to 1 upon T ln initial concentration above the K equal to 1 upon T ln initial concentration of reactant upon concentration of reactant at time t. At time t, when from equation 4.5 ln R1 equal to minus KT1 plus ln R0. Okay, the star is put to show that the time is no longer a 0 second, because time has been increasing since after the 0 second. Okay, so time RB is moving on as the reaction is continue, and here the concentration reactant is being consumed. Okay, so that's why the star is shown for the T1. So ln R1 equal to minus KT1 star ln R0. Then at time T2, ln concentration of reactant, this is a T2. Now this is a different time. Okay, different time, that means concentration of reactant of course been changed. So ln concentration of reactant at time T2 is equal to minus KT2 plus ln initial concentration. Now where R1 initial concentration at time T1 and R1 and R2 is what not initial. It's a concentration of reactor at time T1 and concentration of reactor at time T2. At a different time, of course, the concentration of the reactant will also be different at different time. The concentration of reactor at time T1 and T2 respectively. So when we subtract this 4.12 from 4.11, when we subtract these two equation together, what we get, ln R1 minus ln R2 equal to minus KT1 minus in bracket minus KT2. We can say after subtracting the difference the difference in the concentration of reactant we will get at different time sets. At two different time sets we can get the difference between the two different concentration of a reactant. Okay, then afterwards it is a log. Okay, ln. So after log it will become ln R1 upon R2 equal to K T2 minus T1. Why? Because minus minus become plus. So ln will be R1 upon R2 equal to K T2 minus T1. Okay, and R1 the R1 shows that at a time T1 the concentration of a reactant at time T1 is higher than the concentration of reactant at time T2. So the higher amount of concentration will be always be higher, okay, will always be higher during the division, or on the subtraction will always be the first forward, okay. So now we are now it is rearranged to get a rate constant of a first order. So another equation we are getting is k equal to 1 upon t2 minus t1 ln r1 upon r2. Okay, now the 4.9 equation can be also written, that is ln r upon r0 equal to minus kt. Okay, now first equation which we got, okay, that also can be written, okay. So taking anti-log of both sides, what we get is our rate of a sorry what we get is r in a bracket equal to I in a bracket base to the power 0 e raised to minus kt. That means concentration of a reactant is equal to initial concentrations uh, exponential to the negative exponential power to the negative kt. Comparing equation 4.9 y equal to mx plus c, if we plot Ln concentration of reactant against t, we get a straight line with a slope equal to minus k and intercept straight line with the slope is equal to minus k, intercept equal to ln r0. So straight line with the slope equal to minus k will be there, and it will be intercept will always be equal to the log of initial concentration of the reactant. So first order rate equation we can written in the form of, so the rate constant of first order reaction is k equal to 2.303 upon t log r0 upon rt. Okay, by adding the log in this equation we get k equal to 2.303 upon t log r0 upon rt, and we will often use this formula for the first order of reactions. Another formula is log initial concentration upon concentration of reactant equal to kt upon 2.303. Okay, if we plot a graph between log initial concentration upon concentration of reactant versus time, the slope will be k upon 2.303. Now there's an example for the first order reaction is took, which is ethene hydrogenation. So ethene is a C2H4 unsaturated hydrocarbon. It's been treated with the hydrogen gas. So this reaction will go into hydrogenation reaction. What we get, it's a ethane gas. Okay, so rate is equal to kC2H4. That means the rate of ethene hydrogenation is equal to rate constant concentration of ethene. All natural and artificial radioactive decay of unstable nuclei takes place by first order kinetics. So which kind of reactions, okay, comes under the first order reaction is all natural all natural okay, all natural reactions and artificial radio decay of unstable nuclei takes place by first order kinetics. So which kind of reactions, okay, are first order reaction? Those which are natural reactions such as ethenes was treated with the hydrogenation, so the ethene was getting into hydrogenation reaction, which is very natural. Okay, and another thing is radioactive decay. The unstable nuclei, okay, always undergo decaying process, okay, and due to that several artificial elements are formed. So artificial radioactive decay of unstable nuclei. The unstable nuclei always undergo decay and form a radioactive elements. Okay, so artificial radio decay of unstable element always go under the first order reactions. Now here is a graph plotted for different formula but of the same order, that is first order reaction. Now both of these graphs are the first order reaction, but the formula is used has been arranged differently. Here we can see a plot between L, N, R and T for a first order reactions. Okay, for this graph, the kind of formula I use is actually where LNR, that means concentration of a reactant is to y-axis, LNR0, that means log of a initial concentration of reactant is intercept, and K is equal to minus slope, which means minus slope is a constant, rate constant. So this is a plot between log of concentration of reactant versus time for the first order reaction. Now another graph for first order reactions. What we can observe that the rate that the log of initial concentration of a reactant upon concentration of a reactant against the time for a first order reaction. Here we can see the time is in x-axis and the log initial concentration of a reactant upon the concentration of a reactants is the y-axis. Here the slope is k upon 2.303, which is a constant. Okay. Now here is a radioactive element which is undergo decay process and forming a element. For example, the radioactive element which is unstable is radium. Its atomic number is 88 and atomic mass number is 226. Okay, when it undergo decay, okay, so radium always release alpha particle. The alpha particle is helium with atomic number is 2 and atomic mass number is 4. The element which will form from the decay of unstable nuclear element which is radium, okay, the element which is formed is Rn. Okay, now this Rn atomic mass is 222 and atomic number is 86. Why 86? Because it has lost two electron. Why two electron? Because alpha particle is released from the unstable radioactive element of radium. Now the rate of decay of radioactive element of radium will be rate equal to K concentration of a radium. ठीक है. Now the another example of first order reaction is decomposition of N2O5 and N2O are some more example of first order reaction. तो फर्स्ट ऑर्डर रिएक्शन का पहला एग्जांपल ये है कि जो रेडियो एक्टिव एलिमेंट जो डीके प्रोसेस में चला जाता है, ठीक है, तो वो फर्स्ट ऑर्डर रिएक्शन रहेगा. रेडियो एक्टिव एलिमेंट जब भी डीके हो जाएगा तो वो हमेशा फर्स्ट ऑर्डर रहेगा. और दूसरा एग्जांपल है N2O5 डाई नाइट्रोजन पेंटाऑक्साइड और डाई नाइट्रोजन ऑक्साइड जब डिकम्पोजिशन में चला जाता है तो वो भी फर्स्ट ऑर्डर रिएक्शन ही होता है. ठीक है, यहाँ पे सॉल्व एग्जांपल्स है. ठीक है, लेट अस कंसिडर अ टिपिकल फर्स्ट ऑर्डर गैस फेस रिएक्शन. अब एक एग्जांपल लेते हैं जिसमें गैशियस रिएक्शन हो रहा है। इसमें रिएक्टेंट भी गैस है, प्रोडक्ट जो फॉर्म हो रहा है वो भी गैस है, और ये फर्स्ट ऑर्डर है। ठीक है, तो हम गैशियस रिएक्शंस में फर्स्ट ऑर्डर रिएक्शन में से रेट कैसे डिटरमाइन करेंगे वो हम डिटरमाइन करते हैं। Let P1 be the initial pressure of A and Pt the total pressure at the time T. Integrated rate equation for such reaction and can be derived as total pressure Pt is equal to Pa plus Pb plus Pc pressure unit. तो P1 जो है A का इनिशियल प्रेशर है, Pt जो है टोटल प्रेशर है टाइम T पे है। जो ऐसे सारे रिएक्शन का जो इंटीग्रेटेड रेट इक्वेशन उसे डिराइव करेंगे टोटल प्रेशर Pt इज इक्वल टू Pa प्लस Pb प्लस Pc जो है प्रेशर का यूनिट। Pa, Pb, Pc ये पार्शियल प्रेशर है A, B और C का। इफ़ X एटमोसफियर P the decrease in pressure of A at time T and 1 mole of each of a B and C is being formed। तो X एटमोसफियर डिक्रीज होता है जैसे A प्रेशर में टाइम T पे, और A1 मोल जो है हर B और C का वो फॉर्म होता है। तो प्रेशर B जो है और C जो है वो इंक्रीज होता है। ठीक है, X एटमोसफियर में एट T इक्वल टू 0 एट टाइम T। ठीक है, तो ये जो गैसियस फेस रिएक्शन है जिसमें रिएक्टर और प्रोडक्ट दोनों भी गैसियस फेस में है। ठीक है, तो टाइम जब 0 सेकेंड में रहता है तो A जो है P1 एटमोसफेयर रहता है, B जो है 0 एटमोसफेयर में रहता है, C जो है 0 एटमोसफेयर में रहता है एट टाइम और टाइम T मतलब T 0 सेकेंड से आगे बढ़ गया तो तभी जो है प्रेशर जो है रिएक्टेंट A का वो हो जाता है P1 माइनस एक्स एटमोसफियर, और B जो है एक्स एटमोसफियर, C एक्स एटमोसफियर होता है। एक्स एटमोसफियर का मतलब क्या है कि रिएक्टेंट A का प्रेशर डिक्रीज होता है जैसे जैसे टाइम बढ़ता है, और B और C का प्रेशर जो है वो भी। ठीक है, तो जो रिएक्टेंट ए में जो प्रेशर है उसमें जो एक्स है वो डिक्रीज़ हो रहा है। ठीक है, और बी और सी जो है ये दोनों प्रोडक्ट का प्रेशर है। ठीक है, ना P1 इज़ द Pi इज़ द इनिशियल प्रेशर एट टाइम T इक्वल टू 0। जो Pi है आप देख सकते हैं, तो टाइम T0 पे ही इनिशियल प्रेशर है। ठीक है, तो टोटल प्रेशर रिएक्शन का प्रोडक्ट रिएक्टेंट का वो है Pi माइनस एक्स प्लस एक्स प्लस एक्स माइनस एक्स प्लस एक्स कैंसिल टू Pi प्लस एक्स एक्स इक्वल टू Pt माइनस Pi। तो जो प्रेशर जो है प्रोडक्ट का, दोनों प्रोडक्ट का B और C, तो उसमें जो डिफरेंस है प्रेशर का मतलब टोटल प्रेशर और इनिशियल प्रेशर में जो फ़र्क है वही प्रोडक्ट B और C का प्रेशर है। Pa इज इक्वल टू Pi माइनस एक्स इक्वल टू Pi माइनस Pt माइनस Pi। तो Pa जो है एटमॉस्फेरिक प्रेशर, तो Pi माइनस एक्स, तो x जो है हमें मिला था Pt माइनस Pi, तो Pi माइनस इन ब्रैकेट Pt माइनस Pi, तो P तो 2Pi फॉर्म हो जाएगा माइनस Pt। तो उसमें रेट इक्वेशन जो रेट कांस्टेंट जो है फर्स्ट ऑर्डर रिएक्शन गैशियस रिएक्शन के लिए वो हो जाएगा 2.303 अपॉन T लॉग। इसमें Pi जो है इनिशियल प्रेशर है टाइम T पे अपॉन Pm डिफरेंस ऑफ प्रेशर एट टाइम T। ठीक है, तो 2.303 अपॉन T लॉग Pi विच इज़ द इनिशियल प्रेशर अपॉन 2Pi माइनस Pt। ठीक है, now we will do this half life of a reaction on next lecture. Goodbye.